Hello students, I hope you still remember who I am. My name?
My name is Jeff.
Okay, so here I'm going to walk through with you the exam papers that you have gone through, just a little bit of practice in organic chemistry section. So first we begin with the MCQ, and I hope that you can see through my lenses how you would attempt the questions next time if you are still doing chemistry next time. Okay, so question 1 says, which of the following statements is true about compounds X and Y drawn below? So when I see this, right, first of all, I see X in this case has 2 chiral centers, same for Y. Now, for X, right, there are 1, 3 positions, for Y is the same, 1, 3 positions. And we know that for X, this is, let me just draw it for you, pen is here, so this is 1, 3, and this is also 1, 3. So these two, because of the wedges and the hash lines, these two groups are trans, correct? Trans. And these two bonds are pointing towards you, so it's cis. So we know that these two are not enantiomers. Not enantiomers. Okay? Enantiomers. Okay. And we know that these two are chiral centers, these two are chiral centers. But for molecule Y, we notice that there's a plane of symmetry in here. Do you see the way I draw it? This dotted line. Plane of symmetry. What does it mean? It means that although this molecule Y has chiral centers, but there's a plane of symmetry that exists inside the molecule, so it makes Y a meso compound. Meso compound means what? This is achiral. This is not chiral, but this is still chiral, right? Because there isn't a plane of symmetry within the molecule X. So I look at A. A mixture of X and Y may show optical activity. This means it can rotate the plane polarized light, right? We know that meso compound cannot do that because it is a chiral. So Y cannot, but X can. So if you mix them together, of course it can do the job. So A looks very good, but we hold first, see whether there's a better answer. X and Y are both chiral compounds. Nope, this is not true for Y. We know that Y is not chiral. X and Y cannot be separated by fractional distillation. They could. They could because they are not enantiomers. So they are what we call diastereomer. Diastereomer, which means that they have different physical properties such as melting point, boiling point. We can separate them using these kind of physical separations like fractional distillation. For D, X and Y rotate the direction of plane polarized light to an equal amount but in opposite direction. So always translate in chemistry questions. And when they say that they rotate the plane polarized light of equal amount but in opposite direction, right? They are trying to say that, oh, these two compounds are enantiomers. But we know that they are not. They are not, you see, I put down here not enantiomers. So again, D is wrong. So, tada, A is the answer. Question 2. Which represents the ring flip conformer of this compound? Now, so to answer MCQ, right, there's a strategy because you're being restricted by the 4 options here given to you, or sometimes even 5 or 8 or 10. It doesn't matter, so we just use guess and check. Maybe it's faster for some questions. I hope you can learn from me if you like to. So here for this compound, originally, right, you have 1, 2, 3 tris up. Okay, so I just check first. 1, 2, 3 tris up. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, all 1, 2, 3 tris up, so I can't eliminate anything. Next, 1, 3 are your methyl. So I check 1, 3 methyl, 1, 3 methyl, 1, 3 methyl. Again, I can't eliminate anything. But next, we go in deeper. CH3, this 1, 3, right, is what? Up, and down. See? Up and down. So they are trans, up and down. So after ring flip, remember ring flip is the same molecule. We are just changing the conformer of the molecule. Alright? So we do not change from cis to trans to cis, vice versa. Since the original compound here is trans, up and down, so afterwards, after ring flip, it must remain up and down. Trans. So you see, oh, Same side, down, down, wrong. It is a different molecule. Here, down, up, okay, possible first. It's trans. Here, up, down, possible. Here, up, up, no. This means cis. I don't want. I want the trans methyl. Okay? I know what I want, I write down. Next. We also notice that the OH changed from equatorial to axial after ring flip, because ring flip says that whatever that's originally axial becomes equatorial, whatever that was previously equatorial becomes axial. You see, so OH must be axial now. Ta-da! B. That's it. Question 3. Give the IUPAC name for the following molecule. So again, using elimination, right? Okay, see the options here. They are all 3-isopropyl cyclopentanol. Okay, so there's nothing much to check about the name here except for the 2 chiral centers. Obviously, I'm testing you on this RNS configuration for permutation, so let's check. Now, first of all, which one do we assign as number 1? If you're not sure, the answers give you some clues. It says here 3-isopropyl, so we know that this guy here, isopropyl, must be 3. This is 1. So we check carbon number 1, which has the hydroxy group, which points towards you. So the hash lines does not show must be H, and of course H is the lowest priority among here, these 4 groups. So when the number 4 points away from you, you see this is 1, highest priority, followed by this side, right? The right hand side, so this is 2, and this is 3. So you rotate what? Dun 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 dun. My way, so you rotate anti-clockwise. Anti-clockwise is S, so it's 1S. I want 1S, so wrong. Okay. And for 3, again, hash lines not showing to you, so I just draw down hash lines. Number 4, hydrogen pointing away from you. So again, we do, this is highest priority, right? Agree? Because the first carbon here connects to 2 carbons and an H. So for here, we put CCH. For this carbon, it connects to a carbon and hydrogen. See? Hydrogens, not shown, so CHH. Same for this one here, is CHH. So we know that this guy wins because C, they fight, is a draw, and then the next best card is HHC. Ta-da! We have a winner. Okay, wait a minute. I may have a bad hair day. Okay, hopefully this is better. Okay, it's getting a bit bright here. So yes, so this is 1, and this is 2, this is 3. So we have, one more time, this is 1. Then this side is 2. Then that side is 3. So we do clockwise rotation. This is an R. So it must be an R for this carbon, and it is the option B. Okay, great. Let's move on. Next, question 5. Rank the following from the most to least basic. I give it to you. See, indicated most to the least. So again, I always compare the difference. A, B, C. First up, we look at the functional group here. This is a phenol. Phenols is just slightly acidic. Slightly acidic. Whereas for A and B, they are really carboxylic acid. They are carboxylic acid. We call them an acid, so they must win C. So C must be the least acidic. Tick, tick. Now compare A and B. The difference is this part, the substituent. We know that the best acid is the one that can have the most stable conjugate base. So I always compare the conjugate base. When I got rid of this H, right, I put negative charge. Got rid of this negative charge. NO2 is electron withdrawing. So you can spread and pull this negative charge. Spread around. That means what? Lowering the concentration of this negative charge onto the oxygen, which means that it can stabilize. But for A, this is like a ether group, methoxy group that donates electrons via resonance effect into the ring that will intensify the oxygen negative charge, which will not stabilize it. So in general, we know that EWG increase acidity. Okay, but I've explained to you why is it so. So B is the most. C. Okay, that's the answer. Question 6. Which of the following group has the highest priority in RS nomenclature? Remember, R means what? You rotate clockwise, S means you rotate anti-clockwise, okay? I know you're facing the camera, but you know, if I go to the back, right? Clockwise is R, S is counterclockwise, okay? You do this, turning fingers. So we compare. The first one is still a carbon, same proton number, no fight, right? But we see what it is connected to. Option A. This carbon here connects to a carbon 3 times. So this is a C, C, C. For option B, this carbon here connects to H and twice of carbon, CC. Option C, this carbon here connects to H, H, C. See that? Option D, this carbon connects to H and double bond to a C, so twice SC. So we can see the answer. All of them use the carbon to fight, highest proton number. Next, we can see A is the answer. Please don't go and count the MR, the total number of atoms or what. Okay, learn your Cahn-Ingold-Prelog rule well. Okay, understand it. Question 7. For the following exothermic E2 reaction, which rate equation will be observed? So it says that it is E2. You see the term 2, it means it's bimolecular. You see, I always translate the question. You know, if I'm a student, right, I just translate what are they looking for. Bimolecular means what? The 2 is the rate law. Rate equals to K. The sum of the power must be 2. So I see 1, 1, 1, which is 2, 1, 2, 3, B. Right. How do you get the 2? Bimolecular, 1 mole of each, just B. It tells you it's E2. Why is it E2? Primary RX, no steric hindrance. Strong base, non-nucleophilic. Third, butoxide. This is a T-block, some people call it. Okay, T-butoxide. Just a base. Just a base. Strong base. Strong base. Non-nucleophilic. Okay. B. Question 8. Which of the following anions is the best leaving group? So again, translate, right? Best leaving group means what? Most stable on its own. Right. Most stable. That means it's the, in general, almost equal to the poorest nucleophile. Okay? So here it is nitrogen, chlorine, carbon, oxygen holding negative charge. Which is the most electronegative among these 4? O. O holds negative charge. Fine. Right. He likes it. He likes it. We know that hydroxide is a very good nucleophile. Amide is a very good nucleophile. Carbon is a terrific nucleophile. Think of it in the Grignard reagent. It always reacts. So reactive, so sensitive to water, moisture, any protic solvents. So it can't be C, the best leaving group, because it's such a good nucleophile. So among these options, chloride, halides, which is a good leaving group. We learned that. So it's B. Okay? Again, it's all relatives. You must compare the options given to you. Question 9. What is a IUPAC accepted name for the following compound? Again, first up, I just check. We do not count the S, okay, but we count the I in iso. So this is BMI. Still unchanged from the time I told you about my value the last time around in lecture. For option B, it is BIM. For option C, it is IIM. For option D, it is MII. So we follow the alphabetical order. It can't be D, right? It can't be A, right? So B and C sounds possible. So BIM, IM. So what is it? Again, the difference is the front part. One sec butyl or one isobutyl. Now we know that number 2 must be the methyl group, so this is 2, that's 1, that's 4. So we count 1, 2, 3, 4, lowest numbers there. Number 1, this is a, what was it? 1, 2, 3, right? But in total we have 4 carbons, so it's a butyl, but is it sec or iso? Remember, iso means what? At the end, the terminal end, it branches up. So for iso, right, you will look like this. 1, 2, 3, 4, and then connected to a ring. Okay, so this part is isobutyl. Because towards the end, you have a forking of CH3CH3 bonds. Okay, like that. But in this case, it is a secondary butyl group. So B. Number 10. Which of the following carbocation ions is the most stable? Again, I translate. Most stable means what? Means least reactive. Okay, and then of course carbocation ion I want to have a resonance if possible. And I try to have a tertiary better than secondary than primary. Okay, I call this in mind. And when we give you these structures, please don't take it like a face value that is static. It's not, it's always transforming, because if you have resonance structures, it will try to switch, you know, like a ninja, remember? So A, you may think that, oh, it's primary is bad. Okay, never mind, first we put down primary. But when we draw a resonance structure, we get, pardon. Okay, so back here, when you draw a resonance structure, right, using this kind of double arrow, this becomes a double bond here and a positive charge there. Okay, so now this becomes a secondary. Okay, but you see that the alkene bond becomes what? Di-sub. Di-substituted. 1, 2. See? 1, 2. For the first case just now, it was tri-sub. 1, 2, 3. So tri. Okay. For B, this is a di-sub alkene with a tertiary carbocation ion. And when I do a transformation here, push resonance structure, I get something like this, right? It flows up, it swap positions, the pi bond and the positive charge exchange places. Okay, just like you play musical chair. And this becomes a tri-sub. You see? 1, 2, 3. Tri-substituted alkene, and this is a secondary carbocation ion. For C, there isn't any resonance structure because I can't push. No pushing. So no resonance, just on its own. It's the worst. Most reactively stable. For D, right, this is a tetra substituted alkene. Wow. Tetra. And this is a secondary carbocation ion. When I do resonance, and what happened? I would get this. Okay, so this is again, I didn't do anything. What happened? Ayo, let's try this again. Positive charge here, can circle it for you to see better. Double bond, right? Okay, so this is tri-sub, and this is a tertiary carbocation ion. So let's compare all these three. There's a glitch apparently. Never mind, okay? Remember the scene. One last time. You have to be patient, yeah? That's it. That's it. So remember that. I'm gonna copy the image for you. Anyhow, you see that, right? That was a tetra sub with secondary carbocation ion. There was a tri-sub with a tertiary carbonyl ion. Okay? So you compare primary, secondary, tertiary, secondary. This guy lose, so it can't be A. Then B is tertiary, secondary. D is secondary and tertiary. Same, right? It's a draw. So we look at the substitution. It is di and tri. But then for D it is take tri and tri. So D is the answer. Okay, so D is the answer. Always compare like this. For 11, rank the following conformations in order of increasing stability. Note, the dihedral angle in number 2 is 0 degrees. So I'm trying to say that, right? For 2, this is actually eclipse. So this is eclipse. Eclipse. 1 and 3 are what? Staggered. So we know that eclipse are the most unstable. Unstable means the highest energy. So increasing stability. So number 2 must be the least stable. So I want A or D, right? Then now you compare 1 and 3. For 3, all the bulky groups here are next to each other, all sandwiched, all sequestered together. Very bad, a lot of steric hindrance. But for number 1, you see 2 are closer, but then 1 is further down, further away, right? So this is what we call anti conformation. You see anti opposite. This is gauge interaction. So gauge has a higher energy than anti. Number 1 must be the most stable, so D. Come on, just a bit more, push on. Number 12, which of the following alkyl halide reacts fastest in the SN1 reaction? So again, translate, right? SN1 means what? I want a 2-step reaction. In the first step, I need to generate a carboxylic ion C+. So I'm talking about the stability of the carboxylic ion. It could be a resonance or tertiary carboxylic ion. Okay, so I keep all these words in mind and try to draw them out. Resonance. Now when I cut this part out, I get a positive charge, right? This is a secondary. Okay, alright, can do SN1, but could it be better somewhere else? In this case, when I cut this bond here, it is a primary carboxylic ion. See, CHH with our group. No way, B is out. For C, right? When I cut this, it is, what is it? Again, secondary. So, okay. But for D, when I cut this out, you get a tertiary. You know the answer. It's D. Great. For question 13, which structure below would have the highest energy in the energy profile? Okay, so energy profile, we draw the axis. What? Energy against time, right? Or the progress of reaction. So maybe for SN2 it is this. Ooh, 2-step, right? No! It is 1 step. This is SN1, you see, we have intermediate here. So they want the highest energy. Now from A to B, what happens merely is bond breaking. Bond breaking. So I just cut this bond. Bond breaking is endo. We know it's endo. Endo means what? It gains energy. Phew. So B has higher energy than A. B to C is bond forming. Lone pair donates electron to the C+, you form a bond. Bond forming is exo, means exothermic, means you are giving out energy. So that means what? B has more energy than C, right? So I don't want C. Then next, C to D, it's just merely losing a proton. I know it's bond breaking, but the thing is, because O plus is oxygen taking a positive charge, is not that stable. So to compare C and D, relatively, right? D against B, we know that for D, all the atoms are having noble gas configuration. But for B, this carbon here only has 6 electrons. It's not even octet. So B would be the most unstable, which means the highest energy in the energy profile. So it's B. Number 14, which of the following compounds has the highest boiling point? So we compare and see, right, all of them have similar number of carbon, oxygen, all of them have, they all are carbohydrates. But one key difference is for C, right? You see, it's a carboxylic acid. When you draw it out, it has got 2 sites of hydrogen bonding. On average, you see, 1 and 2. For hydroxy group in alcohol, there's only 1 site. For this, there's not even hydrogen bond. No hydrogen bond. C. Last question, finally. Question 15. Which of the following compounds is most likely to show first order kinetics in a substitution reaction? First order means what? It's a 1. Substitution, SN1. Translate, C+, carbocation ion, stable, carbocation ion. Tertiary, if okay, resonance, if possible. Primary, fail. For B, it is primary. Look carefully. Primary, no good. For D, it is secondary, possible. For C, tertiary. See you. Thank you very much. I'll see you next time.